Good evening everyone, I am Mr. Ish. In this video we'll try to make it a little interesting and we'll talk about derivative statements. We haven't talked about derivatives in a while. We'll present a number of these statements. We just have to say if the statement is true or false and then explain the reasons for that. We're starting here with this one statement. If a function is continuous at a, then that function is differentiable at a. We have to evaluate this as being a true or a false statement. If we think back to that differentiability of a function video, we know the statement to be false. If, however, the statement said that if a function is differentiable at a, then that function is continuous at a, then that statement would be true. This statement is false because if a function such as this exists like this, and here's my a, and we're saying that the function right here is continuous at a, then the function is differentiable at this point. This is a false statement because if supposedly you were to zoom in over here, what you could really end up finding is something like a corner, right? You could have a corner or a kink. You could also zoom in some instances and find a vertical tangent line, right? Vertical tangent line. In both of these instances, if supposedly what was really present here was a corner or a kink or a vertical tangent line, you know you still have a continuity of that function. There's no break in it, but you can do derivative procedures at corner kinks or vertical tangent lines because it's very difficult to establish right and left side limits to be the same over here, and you cannot do slope determinations or rate of change determinations of vertical lines. Hence, just because a function is continuous at a, it does not necessarily mean it's differentiable at a, so this statement proves to be false. Let's evaluate this statement. If derivative with respect to a exists, then limit as x approaches at point a, f of x equals f of a. Is this a true or a false statement? I would have to say that this right here is a true statement. We haven't really talked about the concept of continuity. We've talked about continuous functions, but we haven't talked about continuity. This right here is a true function, and I will present a video on continuity which will address this. The reason why this is a true statement is for the following reason. If supposedly you have a function, and we're not even calling this anything other than just f, and it supposedly happens to have a graph such as this. It could have been anything, but I'm using this. Here's my point A, and we have this little point which falls on this curve at point A. The reason why this statement is true is for three reasons. One, f of A is defined. If you were to put A into this function, you actually get a legitimate value which falls on the curve. It's defined. A here happens to be the domain of this curve. It happens to be within the domain of this curve. So this is right here is one reason why this statement is true, that f of a is defined. Another statement which makes this true is that the right hand and the left hand limits are the same. Right hand limit and left hand limits are equal to one another. If you were to calculate the limit as x approaches a for this function, the right hand and the left hand limits would be exactly the same, and they won't be like a conceptual answer such as infinity, positive or minus. You'll actually come at a true value right here on your y-axis with regards to that limit. And the third reason why this statement is true, that if you were to calculate f of x, put in a value f of x, you would land at this value, let's call it y. If you were to calculate f of a right here and you put it right here on this curve and you determine the range value, it would fall on that same value. Here f of x would actually indeed equal to f of a, and for this reason this statement is also true. But the statement right here in general is true because it satisfies all these three conditions, that the a value is defined, it is within the domain of this function, right hand and left hand limits are the same, that the limit exists as x approaches a either from the left and from the right. You can say x approaches a and this limit is defined. Right and left hand limits are good. F of a is equal to a given range value, f of x is equal to a given range value, and they're both equal to the same value. So for all these three reasons, this statement must be true. We have to show whether this statement is true or false. The derivative of this composite f of g of x is equal to the derivative of f with a g built into it in terms of its composite times the derivative of g of x. The best way to do this is to think about a composite function. When you do the derivative of the composite, you always think about a chain rule, and that's how you should proceed. If u is equal to g of x, because the u is a composite, then function with regards to u is equal to f of u. And that's how you're going to go and proceed using the basic definition. Limit as h approaches 0, you have this f of u. Remember, you're doing d over du and then you're doing du over dx, except you have to break this into two separate limits. you'll have f of u plus h minus f of u divided by h times, right over here, we have to show that this is equal to this. If it isn't, we'll say that the statement is false. Times, now we have to do the du or dx. Limit as h approaches, we have g of x plus h minus g of x over h. We have to take this through. What do we get over here? We get over here something which looks like this. The derivative of f of u multiplied by the derivative of g of x. But we have to resubstitute back what the u was. The u was equal to g of x. So we get something like this. F derivative of f with the composite g of x times the derivative of g of x. And we have something over here which looks exactly like this. So the statement is true. When you're doing a composite derivative, it's going to follow this template scheme. And this statement right here, by means of this procedure, is going to show it to be true. For this statement, derivative of square root of f of x, does it equal the derivative of f of x divided by 2 times the square root of f of x? We have to show if this statement is true or false, and we can do so by using the basic definition of a derivative. If f of x is equal to what we see over here, which is this part right here, square root of f of x, then the derivative of this must be equal to, and we have to use the basic definition of a derivative. Limit as h approaches 0, everything goes right here to the template that we know. F of x plus h minus f of x divided by h. Divided by h. Now we have to rationalize this numerator. So let's rationalize it. Limit as h approaches 0, we'll rationalize it. We have f of x plus h plus square root of f of x divided by f of x plus h plus root f of x. When we do the top part, conjugates, we don't have any intermediate terms. We have what forms over here is this: f of x plus h minus f of x divided by h times this part right here, root f of x plus h plus root f of x. And if you look at this term right here with all of this, from here what we end up getting is this derivative of x of f of x, right? All of these things give you the basic definition of a f of x derivative. This right here, as limit as h approaches 0, you end up having square root of f of x plus square root of f of x. Think about it, these h values here zero out. When you simplify all of this, you have derivative of f of x divided by 2 root f of x. So what does it show? It's exactly showing you what you're seeing over there. The statement must be true. By means of this evaluation procedure, we've shown that anything which looks like this in terms of template derivative, it looked like that in terms of the derivative, and it's true. So we end this video with this last question. We have to show whether this statement, if you take the derivative of f root x, it equals to the derivative of f of x divided by 2 root x. Just by looking at this statement very generally, I believe it will be a true statement, because if supposedly you were to look at something like this, sine root x, and you were to do the derivative of this, you'd use the chain rule, d over du. You'd have sine u and then du over dx. Root x, you'd have cosine u 1 over 2 root x, and you'd have cosine root x divided by 2 root x, which looks just like derivative of f of x divided by 2 root x. So this statement will prove to be true. We just have to show you in proper procedure why it is so. The procedure starts as this: f of x is equal to f root x. Then therefore the derivative of this f of x is equal to limit h approaches 0. Everything will run through this. You'll have f root x plus h minus f root x divided by h. You can rationalize that numerator, and let's do it. F root x plus h plus, and we're using a conjugate over here for the rationalizing. Limit as h approaches 0. There are no intermediate terms, but when you multiply these conjugates, look what happens. You get f square x plus h. See, this f times f is f square, but then root x plus h times root x plus h, just x plus h. Likewise, you have minus f square x divided by h times all of this here in the denominator, f root x plus h plus f root x. The trick over here, what you have to do is you have to isolate from this numerator a single f. If you isolate a single f, you can create within this parentheses f of x plus h minus f of x. divided by everything you still see here in the denominator, f root x plus h plus f root x. Now see, if you combine this term right here in this bubble right over here with this term right here, you've created derivative of f of x. And you have this f sitting out, f times the derivative of f of x divided by everything here in the denominator. But as you take these limits, h approaches 0, you have f root x plus f root x. F root x plus f root x. Again, what have I done over here? I basically, from this numerator here, isolated a single f, and then I was retaining what remained, f of x plus h minus f of x, which I married along with this h to get your derivative of f of x. This basically becomes f times f of x derivative divided by 2f root x. This f right here cancels out with this f. You end up having derivative of f of x divided by 2 root x. And you end up showing that indeed it was a true statement. Not too hard, but slightly tricky, especially this part right over here. This statement expression which develops here in the numerator, you just isolate a single f. You bring out the derivative of f of x from here. This single isolated f will get cancelled right here in this step over here with this 2f root x. This f will cancel out with that. You'll have derivative of f of x divided by 2 root x, and it'll look exactly as you see over there. And then this statement is proven to be true. It was just a bunch of evaluations of these derivative statements, or you can say they were truth statements, and you have to show them to be true or false, and that's what we did. And that's it for this video. Thank you for watching.